Hello. Recall that in the previous few classes we discussed message integrity and cryptographic hash functions. We now discuss another related concept, that is digital signatures. So digital signatures are similar to manual signatures, which we are all familiar with. Recall that manual signatures are extensively used on various documents such as checks, credit card receipts, legal documents, letters, and so on. So a person makes a manual signature to indicate that he or she created a document or agrees with or acknowledges its contents. A digital signature is used to achieve the same objectives for documents in digital form. So a digital signature is the digital counterpart of a manual signature. So what properties must a digital signature satisfy? Similar to a manual signature, a digital signature must be verifiable and non-forgeable. So what do we mean by verifiability and non-forgeability? By verifiability, we mean that it must be possible to prove that a person's signature on a document is indeed that person's signature. So for example, if Alice creates a digital signature, then it should be possible for Bob to verify that this is indeed Alice's digital signature and not someone else's. So verifiability means that it should be possible for a third person to verify that a particular digital signature is that of the person who claims it to be their digital signature. And non-forgeability means that no one should be able to create a person's digital signature except the person himself or herself. For example, only Alice should be able to create Alice's digital signature. Some other person, say Trudy, should not be able to forge Alice's digital signature. So this is non-forgeability. So notice that a manual signature must also satisfy these properties, verifiability and non-forgeability. And likewise, a digital signature should also satisfy these properties. So let's discuss one attempt to create a digital signature. Recall that we discussed message authentication codes or MACs in the context of message integrity. Let's try a similar technique to create a digital signature. To sign a message M, Bob appends a field that is similar to a message authentication code to the message. That is, first Bob concatenates M and S, where S is a secret bit string which only Bob knows, to get this M comma S string, and then computes its cryptographic hash function to get h of M comma S. The signed document is then the original message along with h of M comma S. So M comma h of M comma S is the signed document. Does this scheme achieve the objectives of a digital signature? This scheme does not achieve the objectives of a digital signature. In particular, to create this digital signature, the creator needs to know the secret S, which only Bob knows. So no one other than Bob can create this digital signature of Bob. So the signature is non-forgeable. So it satisfies one property of the digital signature, but it does not satisfy the property of verifiability. Because some other party, say Alice, cannot verify whether this signature is indeed that of Bob. To verify that the signature is indeed that of Bob, the secret S is required, but only Bob knows that secret S. So it is not possible for some third party, say Alice, to verify that this is indeed Bob's digital signature. So in summary, this scheme achieves the property of non-forgeability, but it does not achieve the property of verifiability. So hence it's not a valid digital signature. Let's try to modify this version to create another scheme for creating a digital signature. Now we have the same scheme, except that another user, say Alice, knows the secret S. So Bob uses the same scheme as above to create a digital signature, but now this secret S is known to Bob as well as Alice. So does this modified version achieve the objectives of a digital signature? In this case, we have already mentioned that to verify this signature, one needs to know the secret S. only Bob and Alice know the secret S. So this signature is verifiable only by Alice. But we require that the signature should be verifiable by anyone. So that property is not satisfied by this scheme. Here only Alice is able to verify the signature, whereas we want the scheme to be verifiable by anyone. So this verifiability property fails. And also, since Alice knows the secret S, Alice can also create this digital signature m comma h of m comma s. So someone other than Bob can create the this digital signature. So the signature is forgeable. Alice can forge the digital signature of Bob. So hence, this scheme achieves neither verifiability nor non-forgeability. So hence, this scheme also fails. We want an alternative scheme for implementing a digital signature. So we discussed two different schemes for creating a digital signature. The first scheme operates as follows. Recall that if KB plus denotes Bob's public key and KB minus denotes Bob's private key, then KB plus of KB minus of m equals m. Recall that for RSA encryption and decryption, for RSA encryption, we first apply the public key to the message m to find out KB plus of m. So for RSA encryption, suppose Alice wants to encrypt and send a message to Bob, then she finds out KB plus of m. So this is the message encrypted using Bob's public key, and then to decrypt this message, Bob computes KB minus of KB plus of m, and we showed that this is the same as m. So Bob can recover the original message by decrypting it using his private key. Now, during our discussion of RSA, we discussed that if we apply these operations in the reverse order, then we still get back the original message m. That is, if we start from the message m and apply the encryption algorithm, but with the private key in place of the public key, then we get KB minus of m. And then if we apply the decryption algorithm, but with the public key in place of the private key, then we get KB plus of KB minus of m, and this is the same as m. So if these operations are applied in the reverse order, then still we get the original message m. So we discussed this property, and this was an exercise for you to show during our lecture on RSA. So we now use this property to create a digital signature. To sign a message m, Bob computes KB minus of m and appends it to m. So what is KB minus of m? KB minus of m is obtained by taking the message m and applying the encryption algorithm with Bob's private key to it. So KB minus of m is the digital signature, and it is appended to the message m. So m comma KB minus of m is the digitally signed message. This shows the scheme. This is the original message m. And then we apply the encryption algorithm along with Bob's private key KB minus to get this signature KB minus of m, and this KB minus of m along with the message m, that is the digitally signed message. So is this signature KB minus of m verifiable and non-forgeable? Our claim is that yes, it is verifiable as well as non-forgeable. So it is verifiable because any third person can use Bob's public key, which is well known, to compute KB plus of KB minus of m, which we know is the same as m. So since KB plus of KB minus of m equals m, which is the same as the plaintext message, hence the third person is able to verify that this is indeed Bob's digital signature. So the message along with the digital signature is this m comma KB minus of m. So a third person who wants to verify this message applies Bob's public key to it to get and the result is kb plus of kb minus of m, and if that is the same as m, then the verification is successful. Notice that if this is m and this is suppose this is m prime and this is kb minus of m, then the verification will fail because this kb minus of m is not the it's not the digital signature of m prime. So this is the verification step, and it can be the digital signature can be verified by anyone. So hence the verifiability property is satisfied. Also, is it forgeable? Now, to create this digital signature kb minus of m, we know that we require Bob's private key, but only Bob knows his private key. Since the knowledge of the private key is required to compute kb minus of m, it is non-forgeable. Only someone with the knowledge of Bob's private key is able to compute this digital signature. So since the private key is known only to Bob, it is this signature is non-forgeable. We have obviously assumed that Bob has not shared the private key kb minus with anyone, and it has not been stolen from him. Under these assumptions, the non-forgeability property is satisfied. Now, this scheme has a shortcoming. We discussed that RSA encryption and decryption are computationally expensive operations. Under this scheme, one needs to calculate kb minus of m. That is, the encryption algorithm needs to be run for the entire message m. So public key encryption decryption is time consuming. So hence this scheme is computationally expensive when m is long, because we require to compute kb minus of m. We want a more computationally efficient scheme for creating a digital signature. So to create a more computationally efficient scheme, we use a cryptographic hash function, which we discussed in the previous lecture. So this more efficient scheme is as follows. To sign a message m, Bob first computes its hash h of m, and then encrypts it with his private key to get kb minus of h of m, and then appends kb minus of h of m to m. So m comma kb minus of h of m is the digitally signed message. This shows the scheme. This is the original message m. Bob applies a hash function to it to get the hash value h of m, and then applies the encryption algorithm along with Bob's private key to this hash, and the result is the signed hash kb minus of h of m. And then the original message m along with the signed hash kb minus of h of m are appended, and that's the package that is sent to Alice. So that is the message along with the digital signature. This figure on the right shows the operations that are performed by someone who wants to verify the digital signature. The message along with the digital signature is this: m comma kb minus of h of m. The verifier takes the message part from it, that is m, and then applies the hash function to it to get the hash value h of m. And then the verifier takes the other part of the package, that is kb minus of h of m, and then applies the encryption algorithm along with Bob's public key to it to get h of m, and then compares this h of m with the hash of the message m. And if they are the same, then the verification is successful. So this is the scheme for creating a digital signature. This also works, and it is computationally more efficient. So let's see why this scheme creates a digital signature successfully. So it is verifiable using this scheme. To verify it, someone only needs to know Bob's public key, which is well known. So it is verifiable. And to create this digital signature, one needs to know Bob's private key, which is only known to Bob. Hence, it is non-forgeable. Only someone with a knowledge of Bob's private key is able to create it. So hence, only Bob is able to create this digital signature. Hence, it is non-forgeable. So hence, this scheme also works. It is verifiable and non-forgeable, and it is computationally more efficient than the previous scheme, because to create the digital signature, Bob only needs to find kb minus of h of m. Recall that regardless of the length of the input message m, the hash value is a fixed length message of just a few bits, typically 128 or 256 bits or of that order. So h of m is a short string regardless of the length of the message. So hence it's computationally easy to compute kb minus of h of m. So hence this is computationally more efficient. Now consider the alternative scheme where c of m is a checksum function instead of a hash function. And suppose we use the same scheme with h of m replaced with c of m. So now the message m is combined with the with kb minus of c of m, and that is the digitally signed message. So is this a secure digital signature scheme? So my claim is that this is not a secure digital signature scheme, because as we have seen, for a message m, it's for a checksum function, we can easily find another message m prime, which has the same checksum as the message m. So we can find another message m prime such that c of m equals c of m prime. So once we find such a message, we can replace this quantity with m prime comma kb minus of c of m. The verification will succeed because c of m is the same as c of m prime. So it's easy to modify this message. Someone can easily modify the document, and someone is able to create a digital signature of a message m prime successfully. So hence this scheme is not a secure digital signature scheme. So it's forgeable because someone is able to forge the digital signature of the message m prime, provided that c of m equals c of m prime. So hence this is not a secure digital signature scheme. Now a digital signature is mainly used to indicate that he or she created a document, or to acknowledge its contents, or to agree with its contents and so on. But a digital signature can also be used to achieve the property of message integrity, as we'll see. Recall that in scheme 1, m comma kb minus of m is the digitally signed message, and in scheme 2, m comma kb minus of h of m is the digitally signed message. So which of these schemes, if any, achieves message integrity? My claim is that both of these schemes achieve message integrity. That's because of verifiability, the fact that kb plus of kb minus of m is not equal to m prime when m is not equal to m prime, and the computational infeasibility of finding a message m prime which has the same hash as an original message m. So using these properties, it's left as a simple exercise for you to show that both these schemes achieve message integrity. So if one wants to send the message m with integrity, then one just has to send m comma kb minus of m, or one can send m comma kb minus of h of m, and then the receiver can verify whether the sender is indeed who they claim to be, and whether the message was modified during transit. So both these schemes achieve the property of message integrity. Now recall that the message integrity of a message m can be achieved using a message authentication code as well as using a digital signature. So what are the pros and cons of these techniques, MAC and digital signature? The pros and cons are as follows. Recall that to create a digital signature, one requires encryption, which is time consuming. So that's a disadvantage of a digital signature for creating a message authentication code. But a MAC does not require encryption. So recall that the message authentication code of a message m was this h of m comma s is the message authentication code. So to create this, one does not require any encryption. So whereas a digital signature requires encryption. To create kb minus of h of m, one needs to encrypt h of m using the private key. So that's one trade-off. So the digital signature requires encryption, but a MAC doesn't. So that's an advantage of a message authentication code. On the other side, we have that that a MAC requires the sender and the receiver to have a shared secret, that is the authentication key S. The digital signature does not require the sender and receiver to have any shared secret. To use a message authentication code, the sender and receiver initially have to agree on a shared secret, which will serve as the authentication key S. Subsequently, they can use a message authentication code to achieve message integrity. To compare a digital signature and a message authentication code, we note that a message authentication code can only be used to achieve the property of message integrity. So that is in the context where one sender, Alice, wants to send a message to one receiver, Bob. So then they can have a secret shared key S and then use a message authentication code. If they want to send a lot of messages to each other, then it is efficient to use a message authentication code, because the authentication key has to be created and shared only once at the beginning of the communication. Subsequently, they can send any number of messages using the same authentication key. So in this case, message authentication code is more efficient than digital signature. But a digital signature is more general than a message authentication code. A digital signature of a message can be verified by anyone, not just someone who has a shared authentication key with the creator of the digital signature. So a digital signature is a more powerful scheme than a message authentication code. So a digital signature not only achieves message integrity, but also it is more general and it is more general and it can be used to sign a message, satisfying the properties of verifiability and non-forgeability. So these are the pros and cons between a message authentication code and a digital signature. Thank you.